Okay, let's get started. So moving on to elemental analysis today. So let's talk about elemental analysis. So what's elemental analysis? Elemental analysis is really just something we do with the goal of determining the empirical formula of a compound. Okay, so let's first define what an empirical formula is. An empirical formula is a formula where the subscripts reflect the relative number of atoms of each element in simplest possible terms. So you can refer to an empirical formula as, okay, I'm getting an echo, so let me turn up the mic for now. All right, so just type in the chat box if you have a question. So empirical formula is, like I said, the simplest possible formula for a compound. It simply tells you the relative number of atoms of each element that's in the compound. So for example, if your formula is C6H12O6, okay, that tells you that the carbon to hydrogen to oxygen ratio is 6 is to 12 is to 6, okay? So that means there's twice as many hydrogens as carbon or oxygen. So we can simplify this into a ratio of 1 is to 2 is to 1. So the empirical formula of this is CH2O, okay? So that's not the formula of the compound. Okay, the compound itself has a formula of C6H12O6. So you would call this the molecular formula. Okay, C6H12O6. CH2O is the simplest formula that just tells you the relative number of atoms of the elements present there. So CH2O is your empirical formula. All right. Now, how can you tell that you have the formula you have is an empirical formula? Okay. What you need to do is look at all the subscripts. Okay. And if the greatest common factor of all the subscript is 1, then that is, you already have your empirical formula. And how can you tell that? You can tell if your smallest subscript is a 1, or if none of the subscripts is a 1, what you try to do is you divide all the numbers by the smallest one, and if one of the results is a whole number, then that means you've already got the smallest possible set of whole numbers. So let's look at this question. Is this an empirical formula? C3H6O2. Well, what's the smallest of these? None of these is 1, right? So let's divide all of the subscripts by the smallest number, which is 2. So 3 divided by 2 is 1.5. 6 divided by 2 is 3. 2 over 2 is 1. See, one of the numbers is not a whole number, so this is the simplest formula you can get with the smallest possible whole number. So the answer to this question, we say, is yes, that's an empirical formula. Okay? So compounds, all compounds that have the same molecular formula will have the same empirical formula. Okay? So and the molecular formula will just be a multiple of the empirical formula, a multiple. So for example, if you have a compound with an empirical formula of CH2, okay, that the correct formula of the compound could be CH2, it could be C2H4, okay, it could be C3H6. So any compound that has a formula where the carbon to hydrogen ratio, any compound of carbon and hydrogen, where the carbon to hydrogen ratio is 1 is to 2, would have an empirical formula of CH2. So if you'll notice, this is 1 is to 2. 2 is to 4 is the same thing as 1 is to 2. 3 is to 6 is the same thing as 1 is to 2. So if you have a compound with a formula of C2H4 or C3H6 or C4H8, these compounds would have the same empirical formula. If you had a compound that had a formula of CH2, which you don't, okay, then its empirical formula is also CH2. But there is no known compound. It just so happens that there is no known compound with a molecular formula of CH2. But any compound whose formula would have a carbon to hydrogen ratio of 1 is to 2 will have an empirical formula of CH2. All right. Empirical mass would be the molar mass that's associated with the empirical formula. Since the molecular formula is just a multiple of the empirical formula, then your correct molar mass for your compound would be just a multiple of the empirical mass. So let's calculate the empirical mass of CH2. Carbon, if you look at your periodic table, has an atomic mass of 12.01. So the molar mass of carbon is 12.01 grams per mole. And two hydrogens would be 2 times 1.008. If you add these up, you get how much? That's 12.01, and 2 times 1.008 is 2.016. So that's 14.02. Okay? So we say 14.02 grams per mole is the empirical mass of any compound that has an empirical formula of CH2. All right? So what would be the possible molar masses? Of a compound whose empirical formula turns out to be CH2. Well, if that compound has a molecular formula of CH2, then it's going to be 14.02 grams per mole. If actually that doesn't exist, but that's beside the point. This is just for example. If it was C2H4, that's a multiple of CH2. That's twice as much carbon and hydrogen in your formula. Then the molar mass would be 2 times 14.02 grams per mole. So that's going to be 28.04 grams per mole. If the molar mass is C3H6, then that's 3 times more than C2H2. Okay? So the actual molar mass will be 3 times 14.02 grams per mole. And what's 3 times 14? That's 42.06 grams per mole. Okay, so that's how you can determine that's how the molar mass, the actual molar mass of your compound relates to its empirical mass. All right, so here's a clicker question. Which of the following is least likely to be obtained as the molar mass of a compound with an empirical formula of CH2? Is it 28.1, 42.1, or 78.0? Oops. Ready with clickers? Okay. All right. In fact, I already gave you this example, right? 28.1 is C2H4. 42.1 would be C3H6. And the way you can tell is you just divide by the empirical mass, which is around 14, and see if you can get a number close to an integer, a whole number. So 28 over 14 is 2. 42 out of 14 divided by 14 is 3. But 78 divided by 14, okay, would be very far from a whole number. How far is it from a whole number? 78 divided by 14, that's 5.6, right? So that's too far away. It's halfway between two whole numbers. So this one is least likely to be the molar mass of a compound whose empirical formula is CH2. All right. Now you may be asking, what if you actually calculate these numbers, they are not going to be exactly whole numbers, like the 42.1 divided by 14.02. If you actually did that, Okay, 42.1 divided by 14.02, you actually get 3.003. 03. Okay, although you only have, if you only have 3 sig figs, that's still 3.00. But it's not exactly an integer, but that's okay because we realize that when we do experiments, we will be subject to random error. So you don't expect to get exact integer numbers, but you should get something very close to an integer or a whole number. So going back to the main topic, which is elemental analysis. Okay, the general strategy then in elemental analysis is you try to break down your compound to its component elements. Okay, so you do that in the lab. You find a way to break it down into its elements. And based on the experimental data, you try to determine the relative number of atoms of each element obtained. So you get the count-to-count ratio for the atoms of the elements that are found in your sample. And if you recall, the way we count is by moles, so you can also do a mole-to-mole ratio. So you determine the subscripts of your empirical formula by reducing that count-to-count ratio or mole-to-mole ratio to the smallest possible set of whole numbers. And that would be our general strategy for elemental analysis. So here's an example. If you have a compound of carbon and hydrogen, and let's say you did an experiment and you found that it had 2.500 times 10 to the 22 carbon atoms, that's the count for a carbon atom in that particular sample. And in that same sample, you found that you have 7.49 times 1090 times 10 to the 22 hydrogen atoms. So that's your count-to-count ratio. All right, you're asked for the empirical formula. All you have to do then is reduce that count-to-count ratio into a whole number ratio, the smallest possible whole number ratio. So how do you reduce that to whole number ratio? A good strategy to use is to just divide both by the smaller number. So divide by, in this case, 2.500 times 10 to the 22nd power. So let's do that. You have 2.5 times 10 to the 22nd power. Okay, and this one should just be 1, right? Divide by itself. Okay. And the other one is 7.490. 490 divided by 2.5, and the 10 to the 22nd will just cancel out. So I'm just going to do that, and I'll get 2.996. And you can see this is very close to a whole number, so that's essentially a 3. So we say that our empirical formula here is CH3. Okay. What's the formula of the compound? We don't know. It could be CH3, it could be C2H6, it could be C3H9, and so on. The only thing that an elemental analysis will give you is the empirical formula of the compound. You're going to need additional information to actually determine the molecular formula. And that additional information is the molar mass. Okay? Here's another example. Let's say you have a compound that's made up of nitrogen and oxygen, and in a particular sample of a compound, you did an analysis in the lab. Okay? You determined how much nitrogen and oxygen it has, and you found that, let's say you found that it has 1.90 moles of nitrogen and 3.80 moles of oxygen. Well, that's your count-to-count ratio, 1.9 moles to 3.8 moles. Okay? Remember, we can count by moles. In fact, that's a preferable way to count atoms and molecules. And so, again, you reduce this to a whole number ratio. And the strategy we use is we divide both by the smaller number. Basically, you're making the smaller number, making the small number equal to a 1. Okay, so divide both by 1.90. So this is going to be a 1. 1.90 divided by 1.90 is 1. And 3.80 divided by 1.90 is 2.00. Okay, sig figs here, so that's 1.00, so 2.00. So that means the empirical formula of this compound is NO2. Right? So that's another example. Let's look at another one. You have a compound of carbon and hydrogen. Okay? And let's say a particular sample of that compound you found to have 5.00 moles of carbon and 6.65 moles of hydrogen. So again, what's the strategy here? You divide by the smaller number. So what are we going to divide this by? The smaller number is 5, right? So divide by 5.00. So 5 divided by 5 is a 1. But what is 6.65 divided by 5? That's 1.33. Okay, we don't like that 0.33. That's not a whole number, and that's too far from a whole number. You don't round that off to a 1. Okay, if your number that you get after dividing by the smallest number, dividing everything by the smallest count, if one of the numbers you're getting is too far from a whole number, do not round off. So at this point right here, what we need to do is find something that we multiply it with, so that you get all of these numbers would be, the result would be all numbers that are very close to whole numbers. So if I multiply all of this by 2, let's try multiplying everything by 2, then you're going to get 2.00 here, and that's going to be 2.66. That's still too far from a whole number. That's still not acceptable. So you try another one. You try times 3. Okay, 1 times 3 would be 3. And 1.33 times 3 would be 3.99. Now that is good. That's essentially a 4, right? So now you can say then that your empirical formula is C3H4. Okay, so keep that in mind when you are determining empirical formulas. You want numbers that are as close to an integer, a whole number as possible. Okay, so if you're off by about, 0.0, anywhere between 0.01 to 0.05, that should be close enough. You have to go by your sig figs. Okay. All right. So here is a compound that has 1.200 grams carbon and found to also have 0.4000 grams hydrogen. So what do we need to do to determine the empirical formula here? Now you might be tempted to just divide this by the smaller number, but you can't. This is a gram to gram comparison. What you want to determine empirical formula is a count-to-count comparison or a mole-to-mole comparison. So you have to do an extra step here. You have to change this first to moles and change this one to moles, and then you have a problem that's similar to what we had earlier. So let's review. How do you convert grams to moles? So let's see. 1.200 grams carbon. How do you change that to moles? 1 mole of carbon weighs how much? Check your periodic table. It's 12.01 grams, right? So what is 1.200? Yeah, divided by 12.01. Okay. Now always use at least 4 sig figs in your molar masses, all right? When doing this, 200 divided by 12.01, that gives you 0.09992. Okay, 4 sig figs, 0.09992, because you have 4 sig figs in 1.200. That's why you need at least 4 sig figs for your molar mass. Okay. So this is 0.09992 moles. We do the same thing for hydrogen. Okay. So what do we have for hydrogen? We have 0.4000 grams hydrogen. What's the molar mass of hydrogen? 1 mole of H is how many grams? You look it up from your periodic table and you should find 1.008 grams per mole. Yeah, okay. So grams hydrogen cancels out. That gives us moles of hydrogen, which is, what would that be? 0.4 divided by 1.008. That's 0.3968 moles. Okay. So 0.3968 moles of hydrogen. It's 4 sig figs again, okay? So now that we have our mole-to-mole comparison, we can now determine the empirical formula. How do we do that? We divide by which number? Okay, you divide by 0.09992, and what do we get? This is going to be a 1, right? And 0.3968 divided by 0.09992 is 3.971. Okay, and that is close enough to a whole number. That is essentially a 4. So the empirical formula of this compound is CH4. Okay? Okay. So that's how you do it if you're given if you have the amount in grams. And typically that's what you'll have in the lab. Okay? Because we don't have a mole meter in the lab. Here's another example. You have a compound that's made up of potassium, chlorine, and oxygen, and it's found to be 31.9% potassium and 28.9% chlorine. Unless otherwise specified, this is by mass, percentage by mass. Okay? So another way of saying it is to say that 100 grams of this compound contains 31.9 grams of potassium, and 28.9 grams of chlorine. How much oxygen does it have? It's got oxygen too. You're given the percentage of potassium and chlorine, so how do you determine how much oxygen you have? Well, all those, okay, so they should add up to 100, right? So what's the answer here? How much oxygen do we have? 39.2? Okay. Let's verify that. Okay, so 100 minus 31.9 minus 28.9, 39.2. All right. So this is similar to the problem we had earlier, except that we have 3 elements, so potassium, chlorine, and oxygen. So you have 31.9 grams is to 28.9 grams is to 39.2 grams. Okay? Now what do we do next? These are gram comparisons. We want a mole to mole comparison, so we have to change this to moles. Moles of potassium, moles of chlorine, and moles of oxygen. So, okay, so 31.9 grams of potassium. How do we change that to moles? 1 mole of potassium. What's the molar mass of potassium? Check your periodic table. What would it be? 39.09? Okay. So 39.09 grams per mole. So what's 31.9 divided by 39.09? Let's see. Oops. Oh, lost my calculator. Okay. 31.9 divided by 39.09. So that's 0.816 moles of potassium. Okay, so this is 0.816 moles of potassium. What's the next thing we need to do? We need to change chlorine this time. Okay, so let's do chlorine. (28.9 grams of chlorine). Change that to moles. 35.5. Okay. I think you have to do one more sig fix. It's 35.45, right? 35.45 grams of chlorine. So 28.9 divided by 35.45. That gives us 0.815. Please sig fix 0.815. And then finally, we change grams of oxygen to moles of oxygen. Right, so we do 39.2 grams of oxygen times 1 mole of oxygen has a mass of 16.00 grams. So what's 39.2 divided by 16? 39.2 divided by 16. That's 2.45. Good. Okay. 2.45 moles. And now that we have the mole to mole ratio, what do we divide these by? Which one is the smallest number? Okay, so you divide all of these by 0.815. So this is going to be a 1. This divided by 0.815 is how much? .00, and this one divided by 0.815 is 0.816 divided by 0.815 is 1 point something. Should be very close to 1, right? 1.001, so 3 sig figs, that's 1.00. So what is the empirical formula of our compound? That's 1:1:3, right? So 1 potassium, 1 chlorine, 3 oxygens. So KClO3. That's how you determine your empirical formula. Okay. Combustion analysis is something we do for what we call organic compounds. These are compounds containing carbon and hydrogen, and it also works for compounds that have one other element besides carbon and hydrogen. Okay? In combustion analysis, what you do is you determine how much carbon and hydrogen you have in a sample by burning the compound. You burn the compound, and then every carbon that you have in your compound combines with oxygen from the air, will give you carbon dioxide. Okay? And every hydrogen that's in your compound ends up being water. So this is carbon in the compound, Your hydrogen in your compound will combine with the oxygen, any oxygen that might already be in the compound, and with the oxygen from the air, and gives you water. Okay, so based on the amount of carbon dioxide and water produced, you can calculate how much carbon was in your sample and how much hydrogen was in your sample. Okay? And in fact, let me illustrate this with one of the simulations that I posted on Moodle. Okay, let me see if I had that here. I think I have stoichiometry, no, elemental analysis right here. Oops. Okay, this one right here. Oops. Run this time. Let me see if I can have it. Okay. So here's a simulation. Okay. So you run your compound through a furnace. Okay, you burn your compound and then you get your water and your carbon dioxide comes out as your products. And then you run it to a trap that will trap the water, and then you run the rest of the gas into another trap that will trap the carbon dioxide, and you can weigh the water and the carbon dioxide produced by the reaction. So let's select a random sample. This compound contains carbon and hydrogen. Okay, the mass of this sample is 0.471 grams. We're going to burn the sample. So it's oh, wait a minute. Oh. Let's try it again. Let's tear this. Okay, so let's burn our sample. Let's pick another sample. Let's pick a random sample again. Okay, so we have to tear our balances first to make sure we get the right amounts of carbon dioxide and water. Okay, so let's say you have 0.491 grams of sample. Let's burn our sample. So you're collecting water here, you're collecting carbon dioxide, and these are the amounts that you got. Okay, so 0.308 grams water, 1.005 grams carbon dioxide, and then you have 0.491 grams of sample, the original sample. Now this particular compound contains carbon, hydrogen, and oxygen. Okay, we'll sample of carbon, hydrogen, oxygen, and according to this simulation, you got 0.308 grams of water, 0.308 grams of H2O, and 1.005 grams of CO2. Okay. All right. So what do we do now? We figure out carbon. Okay. So we change 1.005 grams CO2. Change that to moles. 1 mole of CO2 is 44.01 grams. And then you say you have 1 mole of carbon in 1 mole of CO2. That gives you moles of carbon. All right? And then you do the same thing for hydrogen from water. So your hydrogen comes from water. So you have how much water did we get? 0.308. 0.308 grams of water. Change that to moles. 1 mole of water is 18.02 grams. And then you change that to moles of hydrogen. There's 2 moles of hydrogen in 1 mole of water. Okay? So what would those numbers be? Carbon would be 1.005 divided by 44.01. That gives you 0.02283. Okay? 0.02284 moles of carbon, and your hydrogen in this case will be 0.308 divided by 18.02 times 2. That gives you 0.03418. Okay? This is carbon. Let's change that to moles. How do you change grams to moles? Multiply by the molar mass, right? So you have 0.02284 grams carbon times 12.01 grams per mole. That gives you 0.274 grams. And your hydrogen, let's change that to grams. 0.03418 times 1.008. That gives you 0.0345 grams. Okay? So how much oxygen do we have here? This compound has oxygen? Yeah, it has oxygen. So to figure out the oxygen, you just subtract from the total, which was 0.491, minus 0.274, minus plus, and 0.0345 grams. So the mass of oxygen is, so 0.491, oops, what did I just do? I need a calculator. 0.491 minus 0.274 minus 0.0345, that gives you 0.1825. Okay. 3 sig figs grams. So change that to moles. 0.1825 grams oxygen. 1 mole oxygen is 16 grams, 16.00 grams. That's how much? 0.1825 divided by 16, that's 0.0114 moles of oxygen. Okay? So your ratio is 0.0274 to 0.0345, I'm sorry, 0.02284, 0.03418, and 0.0114. So let's put them all together. Moles carbon is 0.0382284. Oh, I just lost my hydrogen. How much hydrogen did I have? Maybe I can undo that. Oh, there it is. Yeah. So let me clear this out a little bit so it's easier to see. Okay. And my oxygen is 0.0114 moles. Oxygen. So what do we do now? Divide everything by, what's the smallest number? 0.0114, right? So let's do that. Carbon, hydrogen, oxygen. This is 0.274. This is 0.0345, and that's 0.0114. Divide everything by 0.0114. This is going to be a 1. What would that be? 0.0345 divided by 0.0114, that's 3.03. And this one, 0.274 divided by 0.0114, that gives you 24. Oops. Oh, 0.027. The carbon, 0.022, oh yeah, 0.02284, I'm sorry. This is 0.02284. That's, you need mole to mole to mole, okay? So 0.02284 divided by 0.0114, that gives you 2.00. So this is 2.00. So what's the empirical formula of our compound? It's going to be C2H3O. Okay? What's our empirical mass? Would be 2 times 12.01, that's 24.02. 3 times 1.008, that would be 3.024. And an oxygen, 1 times 16, 16.00. Our empirical mass is 24.02 plus 3.024 plus 16, that's 43.04 grams per mole. Okay? Now if you go back to that problem, it actually tells you that the molecular mass or the molar mass is 172. So the molar mass is given as 172. So with that additional information, grams per mole, we can determine the actual molecular formula. Because if you divide 172 divided by 43.04, 172 divided by 43.04, that gives you 3.996, which is essentially a 4. So the molar mass is 4 times the empirical mass. So the molecular formula would have 4 times the subscript. So 2 times 4 is 8. 3 times 4 is 12. And 1 times 4 is 4. So this is your molecular formula. All right? So that's how you would do it. So let's stop this recording.